Here I'm going to do examples of looking at sequences and limits, looking at a sequence and see if this sequence converges, if it does have a limit as n goes to infinity. One thing I won't use in Stewart's book, this is something where in the main section on sequences, he brings in the official careful definition with epsilon and n. It's analogous to how you do a careful definition of a limit of a function. In these videos here, I'm not going to talk about that, but I have some videos about the careful definition of a limit and why that's important and useful in various cases. We do still have to be careful and justify carefully whether something has a limit, but it's not going to be going back all the way to the definition. It's going to be using known facts about simple sequences and then some of the theorems that build on that. But we won't go back to the absolute definition, definition 2 in Stewart's book. So what could we do with this one? This is a very common situation where it's a function that would make perfect sense, and we know what it does. We know a lot about it if we defined it as a function of x. Now we'll see examples where that just really doesn't make sense, or it would be too hard to define it as a function of any real number. But if it does, we have theorem 3 in Stewart, which is that when you can do this, the limit as n goes to infinity of an. That's just exactly these values. It just happens to be that we don't put in anything that's not an integer, is going to be the limit as x goes to infinity of f of x, if they exist. And if this doesn't exist, if this limit doesn't converge, then this limit doesn't converge. So they just go in tandem. Okay, so well, actually, that's not technically true. This could diverge maybe just on the values of x that aren't integers. So let's be careful about that. If this converges, let's just do it a positive statement. If this converges, then if this limit exists, then this one does exist and is equal to that limit. So, and that's what's going to happen in this case. We know that the limit as x goes to infinity of x squared over 3x squared minus 20x minus 100. We're going to multiply by 1 over x squared top and bottom. That's because that's the degree of the denominator, and denominator is the trickier place, so that's what we want to tame and make simple. 20 times 1 over x minus 100, 1 over x squared. That guy goes to 0, that guy goes to 0, and so the limit exists and is 1/3. So you might want to emphasize, yes, this limit exists. The sequence converges, and I also know the numerical answer. So let's look at another example. I'll do a few in this video and then break it into parts, do some more. So that's a nice thing. We know a fair amount about taking limits of functions of a real variable. If you can do that, that's great. So let's do something, just a variation on that. So let's take that exact formula, but multiply it by like a -1 to a power. -1 to the n minus 1 is a common one. 3n squared minus 20n. Notice that the minus 20 and the minus 100 had no relevance at infinity, as we usually expect. Make sure that's more visible as an n. Because when n is big, it was this term in the denominator that's dominating. Okay. Now, does this one exist? Well, the -1 to the n minus 1, if you try to make that like a -1 to the x minus 1, that's pretty freaky to have negative numbers to weird exponents. So you really can't do that. But let's just think about what this does. Because we know that this part, that part gets very, very close to 1/3. What are these numbers doing? What is this doing? Okay, that's going to create a sequence that whatever it does at the start, it's going to settle down to something that's very close to 1/3 half the time and very close to -1/3 half the time. And it's going to become very, very much like the whole thing is going to be very close to just -1 to the n minus 1 times the constant 1/3. Rather simple, but definitely not convergent. This does not settle down to a limit. So this diverges. Sometimes, you could just say it's sometimes approximately -1/3 and sometimes approximately 1/3. And never settles down. And that's a pretty good justification. Let's do one more before I switch to a new video. So those alternating signs, that can be a sign that you might not converge because you diverge by alternation. Let's look at the limit as n goes to infinity of n squared tangent 2 over n. So often when you look at these, you want to just do a rough reasoning first about what if n is really big, is there a good approximation, that kind of thing. And then see if there's a tool that makes that more precise. When n is really big, 2 over n is really small. So we're taking, if we look at just the tangent function, one of the things we know about that is that tangent of x is approximately x if x is small. This is a great example of using linear approximations. Okay, so this is going to be really close to 2 over n. And then, actually, I want, let's make it 2 over n squared. I think that's the one I really wanted. I just misread it. Okay, but still, if n is big, then this is very, very small. This tan essentially doesn't do anything. Okay, it really should come close to canceling out and give something very close to 2. So how can we do that? Well, once again, this is something that makes sense as a function of a real variable, and we can use any of our techniques for taking limits of a real variable that we want. So we could just look at the limit as x goes to infinity of x squared tan 2 over x squared. And that would be an infinity times 0 type, and we could do L'Hopital. A little awkward and unnecessarily so, because what we could do, instead of just saying n, just replacing n with x, we could do something a little more creative. Let's say, let's look at the limit as, say, t goes to 0. Let's just do one more transformation and say t equals 1 over x equals 1 over t. So we're changing variables in a limit, which is a really powerful technique. As x goes to infinity, t is going to go to 0. That x squared is now a 1 over t squared times tan of the 1 over x squared is just t squared, so we get 2t squared. Oh, actually, you know what? Let's just say x squared. That's better. That's just even simpler. 2t. There we go. That's very nice and simple. If we let t sort of hide the complexity, part of the complexity of the problem, the thing that's in common, this is always where you do substitution, you're seeing x squared here, and you'd rather not have this be a reciprocal inside a trig function, so you hide that all here. Why does that work? It's simply because as x goes to infinity, then t is going to go to 0. And this is a continuous function, so this had better be continuous for this trick to work. And it has a known limit as x goes to infinity, namely t goes to 0. Okay, so this is just going to be equal to that. So this is something we could do, even if we were interested in this as a real variable. This is a good technique to do this, to make the L'Hopital story simpler. We're still going to do that in a second, but it's going to be simpler. And it's also going to tell us this, since this is equal to this guy, it's going to tell us whether it converges and what it converges to. And our strong guess is it's equal to 2. Okay, now we're in a nice L'Hopital situation. This is 0 over 0. We use L'Hopital. Remember, always check that L'Hopital really does apply, instead of just saying, oh, I've got a quotient of 2 things, I'm going to use L'Hopital. It might not apply, and you could get a totally wrong answer. Secant squared of 2t times a 2 for a chain rule over 1. Secant squared, when t goes to 0, that's just 1 over cosine squared. That just goes to 1. And voila, it's equal to 2. Okay, so we could have done L'Hopitals directly on this thing, and it's not ridiculous, but you get a bunch of unnecessarily kind of chain rule stuff out of it. And this is something that you really want to get used to, of if you can see a substitution to make this formula simpler, that's a great idea. But you just have to make sure that you know the relationship between the variables and know what happens when the old variable goes to whatever that it was going to. What is the new variable going to? If I had said the limit t goes to infinity here, it would have been totally ridiculous. Because as x gets big, t doesn't get big, t gets small. So I'll stop it there and do more examples in a second part.